Hello once again, this is Skip, Victor Echo 6 Bravo Golf Tango, with another crazy project to show you. After having good success on the higher frequencies for moon bouncing, I thought I'd drop down to the lower band here on 432 megahertz and give me another reason to do some more experimenting with PIC controllers. So to start with, I had to build up some kind of rotor system. I am a firm believer of using what I have, and I happen to have these two large bearings, so the aluminum hubs had to be lathed first. Two of these bearing hubs were going to be required, and the inside was homed out to fit the pipe that I had in mind for the project. Then some kind of stand or carrier was built to hold the bearings and their hubs, and the large pipe for the rotor was inserted and checked for rotation. Now it's time to try and get some drive power up to this pipe. I took a small sprocket, laid out the center of it to fit around the pipe, and bolted it to one of the hubs. My plan is to use a stepping motor to drive this shaft. I've never used one of those before, and I've always wanted to play with one, so I had to build up some kind of a sprocket system to get the chain up to the main pipe. Well, that stepping motor didn't work so good, so I had to come up with a new idea. Again, a true believer of using what I have at hand. I have these globe motors, which are a small DC motor with a huge planetary gear system on them. I was able to take one apart and turn the commutator shaft down to make an adapter for it. These globe motors have quite a planetary system in them. I was able to calculate that I only needed one section. This would give me enough torque when coupled to this new stepping motor to drive the new shaft of the rotary system. So I changed it up to the system and gave it a test with my temporary driver. Much more torque than I had before. Kind of got ahead of myself here. I already had the twin dipole antennas built on the reflector and swept and tested. So next I had to build some kind of a flange for it to mount to this large rotating pipe. Again, using what I had on hand, I was able to lathe, mill, and weld together a flange system that would clamp to the reflector and attach to the back of the rotating pipe. So with the motor and rotating system built, next was the building up the chassis and the control system, etc. All the parts were mounted on an aluminum plate that was cut so that it would fit into the feed mount of the dish. A custom enclosure was built to hold the PIC circuit, and a bracket on the outside to hold the Amphenol connectors for the interconnection to the feed mount. The RF relays were hardwired into the preamp and wired into the DB25, which goes into the PIC circuit. External wiring that goes up to a front terminal strip for the stepping motor and to the home switch, which is connected to the front bearing hub. A special cable clamp was built so that this would slide down inside the main pipe and could be bolted solid so that when it rotates, the twist wouldn't try and undo the end connector that's connected to the dipoles. To program and operate this rotary feed, a custom console was built. There's a PIC circuit inside which communicates with the feed, and this is where you set up your transmit receive set points and automatic or manual mode operation. I built a new sequencer for this feed so that all the cabling would plug into it directly from all the other racks and be straightforward enough to operate. Okay, it's time to show you some of the basic operations of this new feed assembly. The panel of the control console is too small to get all the labeling, so I just have a cheat sheet labeled on a piece of paper that sits in front of it. Okay, when we first power this system up, it goes into a default calibration mode, which sets the rotation at a 0 count on the pulses of the stepping motor. This is now the negative 90 degree position as indicated on the LCD. Now, being in the manual mode, I'll move the rotor forward through its full rotation from negative 90 to positive 90 and a little beyond. At 0 degrees, the dipoles are exactly at horizontal polarization. As the dipoles swing past positive 90 degrees, we've done the whole 180 degree swing from negative 90 to positive 90. It's gone from vertical to horizontal to vertical polarization. At this point, I'll reverse direction and letting the rotor go back to 0 degrees at the full horizontal polarization. Okay, I've started reversing the rotor back to negative 71 degrees, which I will use as my receive set point. Here I've pushed the button to enter the negative 71 into the receive set point as indicated on the LCD. Next, I'm moving the rotor back up to a position of 10 degrees positive. This will be the transmit set point. Transmit set point entered as shown on the bottom left hand part of the LCD. With the two set points entered, I'm going to push the auto mode button next. Immediately it rotates over to the receive position. I ground the push to talk input and immediately the rotor switches over to the transmit position. So as I ground the push to talk line, the rotor switches back and forth between transmit and receive positioning. After that, I push the number 1 button and it switches the controller out of manual auto back to your straight manual mode as indicated on the top right hand part of the LCD. Again, this next part I'm going to try and show you how the calculations are done in the feed circuit to come up with the geometric transmit position. The first thing you have to know is what is going to be the geometric polarity of the station you're trying to work. After I've tuned the antenna back and forth for the best receive signal, I've identified the station as being somewhere in the Great Britain area. So I take my mouse and click on the British Isles on the map here, and it comes up with station 2 polarity as 69 degrees counterclockwise. Now with these two set points, I know that my best receive was around 62 degrees, and that the station 2 geometric is negative 69 degrees. I can enter these into the controller as the two set points I need for the auto mode setup. Any polarity angle that shows up as a counterclockwise is entered as a negative value. Now the transmit angle in this case shows up as a negative 200. Well, we don't want the antenna rotating back and forth that far, so the polarity is the same in one angle as it is 180 degrees from it. So we take that negative 200 and add it to a plus 180, and it comes up with a negative degree geometric transmit position. And that's what the feed will calculate and position, which in this case comes up as a negative 20 degrees for the geometric transmit position. Okay, hopefully that wasn't too confusing. So now we'll try and simulate this in real time and show you how it works. This view is the other part of the project. It's the Visual Basic display that I've created, which shows me the antenna status and what's going on with it. So I've started with the antennas in a horizontal position, which is indicated as 0 degrees on the display. The first thing to set is to make sure my set point entries is in the geometric mode and not the manual mode. And this is done by pushing the button on the control console. So next I'll move the antenna to find the best receive signal and then enter that set point. A little peeking back and forth, and I found it at 60 degrees, and I've entered it into the receive position as indicated. So now that I know that the geometric positioning for station 2 is negative 69 degrees, I'll rotate the antenna over that position and enter it into it as the geometric set point. And it's entered as negative 69 as displayed. So the set point's done. All there's left to do now is switch it into full auto mode. Immediately it rotates over to the receive position. The geometric transmit position is also displayed now. The transmitter has been keyed and it switches over to the transmitting position. So as I key and unkey the circuit, it'll go between the best receive of 62 degrees and then switch, as I key it, and switch over to negative 20 degrees in the calculated transmit position. It'll continue to do this until I stop. So we'll say we're done with the auto mode position. I'll push the button, it'll switch back into manual mode. Then I push the next button and I switch the set point entry into manual mode also. So that pretty well wraps it up in kind of a real-time demonstration mode here in the shack. Here are a few pictures of it hanging on the dish that I did on a test session here earlier this year. This is probably the heaviest feed I've had of all my feeds. It weighs an area of 26 pounds. And the dish feels it, but it has no trouble lifting it. So a little bit more testing to be done to see if this geometric auto mode works. If it doesn't, we'll switch over to manual mode and just have some fun.